Hi, I'm Rodrigo Luker. I'm a postdoc at the CCA, where I work on time series analysis, astronomical statistical analysis, and various other things, mostly related to exoplanets and stellar variability. But in my work, I use Gaussian processes a lot, and that's what I'll be talking about today. And hopefully by the end of this lecture, I'll be able to convince you that you too should be using Gaussian processes to fit your data and to do inference. So before I begin, I'll just say, so this lecture is going to take place on an iPad, essentially, kind of like a board work lecture. And so feel free to pause as needed. This lecture follows pretty closely the first Jupyter notebook on the GitHub page for today's lectures. And I'll pause frequently and point out places in the lecture that correspond to some of the exercises in that notebook. Now, there are two notebooks on the GitHub repository. The first one is the one that follows this lecture. The second notebook, you should have all the information you need at the end of this lecture to tackle the one problem in that notebook. That problem's a little more involved. It's using everything that we've learned to infer something about a data set. And in this case, it's a transiting exoplanet data set. So there's an exoplanet transit in there. And we're going to use a Gaussian process to infer something about the presence of other planets in the system. Like I said, that one's a little more involved. And so, you know, there's several resources that I point to, especially the documentation of a lot of these GP codes that are out there. I link to them in the notebook. But I will say, if you get stuck at any point, there is a folder in that repository called Answers, and you're welcome to click there. It has the answers to all the exercises in the two notebooks. If you'd like, you can also email me. My email is rodluker@gmail.com, and I'm happy to answer any questions or help you through the problems. Great. So, like I said, so Gaussian processes are an extremely powerful tool for data analysis. Specifically, they're a non-parametric tool. They're super useful, especially in cases where you're trying to model something that you don't fully understand. A lot of times in astronomy, we're looking for signals in the presence of noise, in the presence of other signals that we may not even be interested in. We kind of just want to, you know, pretend they're not there or marginalize over them. That is ultimately the best application. One of the most powerful applications of Gaussian processes is marginalizing over nuisance signals. So an example of this is if I'm looking for a transiting exoplanet, or if I'm interested in modeling stellar flares, whatever it is, there's usually detector systematics or stellar variability that's significant. It's a significant component of my data, but I kind of want to remove that in order for me to analyze this other signal that I'm interested in. And so that's what we're going to talk about later, is doing inference with Gaussian processes. The cool thing about these GPs is that they're equipped with a likelihood function. That is the probability of your data, given your model, marginalized. So regardless of everything that the systematics are doing. And we'll talk about that in a little bit more detail later. The other thing that Gaussian processes are useful for is prediction. So if you have gaps in your data, or if you'd like to extend your data into the future or back into the past, you can use Gaussian processes for extrapolation or interpolation. And so, you know, typical examples of where you might use a Gaussian process is if you're tracking the value of some stock over time and it has some strange behavior, and maybe you're right there, and your question is, well, should I buy or should I sell, right? Like, is this thing going to keep going up, or is it going to suddenly plummet? Now, I don't know what this function is doing, right? Like, there's no, you know, algebraic or any kind of function that looks anything like this, right? I don't know what the parametric form for what this stock is going to do is. And so this is a good application for a GP, because you're essentially learning what that form is from the data and using that information about the covariance of the data. And we'll talk a little bit more about that. We're using that information to predict into the future. So this would be like the prediction application of Gaussian processes, right? So like predicting into the future, like putting some kind of confidence interval in what you think this function is going to do. The other thing that I mentioned is using this for inference. So if you have some stellar data, you have some star with spots on it that's rotating, and imprinted on that is a dip, you want to have some way of saying probabilistically what the probability of that being a transit of an exoplanet, right? So like if there weren't any stellar variability, right, maybe this would look as nice and clean as that, which is what we'd expect an exoplanet transit to look like when a planet goes in front of the star and blocks its light. But in the presence of the stellar noise, we need a robust way to, first be confident that we're seeing an exoplanet, but also to be able to measure things like the depth of that dip or the duration of that dip in the presence of all these extra wiggles, essentially. So, all right, so I've told you what Gaussian processes can be used for, but let's take a step back. Let's start from the beginning. And before we talk about Gaussian processes, it's very useful to just talk about Gaussians and the Gaussian distribution. Now, most of us are probably familiar with the Gaussian distribution at some level. If you've ever looked at astronomical data and you have a data set that has error bars, almost always those error bars imply a Gaussian distribution. They imply that your data, your observation, is made at a point, but that's not an absolute truth, right? That observation is subject to detector noise, to just counting Poisson noise. It's subject to uncertainties due to like anything related to the observation itself. Usually in astronomy, we can make the approximation that that data is normally distributed or distributed according to a Gaussian. And so those error bars are the width of the Gaussian or the standard deviation of the Gaussian that kind of spans where you actually believe the true value of your observation to be if you didn't have noise. So, let's be a little more formal about this. Let's talk about the Gaussian distribution. And we're going to talk about it in one dimension, which is the simplest possible case. And one of the things we're building towards is going to be to talk about this in many dimensions. And if we get to an infinite number of dimensions, that's when we truly have a Gaussian process, but we'll get there. So this is a Gaussian distribution in one dimension. Now, we may be familiar with the shape of this distribution, right? It's the probability distribution, it's probability of some variable x as a function of x. And it looks something like a familiar bell curve. So a Gaussian in one dimension has two properties. Those properties are the mean, which is the central value, and the standard deviation, which is some measure of the width or the dispersion of this Gaussian. That's labeled sigma. And so this is called the standard deviation. Quite often, in fact, later in this lecture, we're going to talk a lot about the square of sigma, which is known as the variance. And this ends up being a much more fundamental property of the Gaussian, especially when we go up to higher dimensions. Okay, now that's what it looks like, but if we were to actually write it down mathematically, the notation for this would be something along the lines of the probability of x given a certain mean and a certain variance is equal to, we have some normalization constant down here, That's just setting whenever you have probability distribution, you always need a normalization constant because that distribution needs to integrate to 1. That's almost always that's what you want, because your value of x has to be something, right? And so the probability of observing some value of x has to be 1. And that corresponds to the integral of the distribution over all possible values of x has to be 1. So that sets what this normalization constant is. But it usually don't have to worry too much about it. The important thing is that it's distributed as of e to the power of something like this, e to the minus 1/2 x minus mu over sigma squared. A lot of us probably have seen this parameterization before. But this functional form here is that blue curve right there. Now, another way to state what I just wrote in shorthand is to say that x is distributed as a normal distribution. It's a fancy n. And in this notation, the normal distribution has 2 properties. It has a mean and a variance. Okay, that's just shorthand for the Gaussian distribution. Okay, so I'll also say I'll make these notes available as well, so you don't have to pause them all the time. You can just refer back to them, and I'll put them on GitHub. So this is in 1 dimension. It's fairly straightforward. Let's consider going up in dimensions. So let's go to a couple dimensions. So let's look at the Gaussian distribution in multiple dimensions. Now, we've all probably encountered this too. And so I mentioned error bars earlier. And quite often you might have a data set. So say you have some measurement y, and let's say it's a function of time, because that's usually what astronomers have on the x-axis. And so let's say that I make a measurement here, a measurement here, measurement here, measurement here, and I have error bars. Each of those error bars implies a Gaussian distribution with a certain standard deviation, right? This is the standard deviation here of the Gaussian, and with some mean. Now let's say that, that this is time 0, this is time 1, time 2, time 3, and so forth. Okay. Each of these is a Gaussian distribution, so I can say that my first observation, right? So like this one here, okay, is y0, and it's distributed as a Gaussian with a certain mean and a certain standard deviation. Okay, and then y1 is distributed as a Gaussian with a certain mean and a certain standard deviation. And the mean here would correspond to the true value of whatever process this is that we don't know, because all we can measure is the noisy version of it. But we observe all of these data points, not just individual data points, and we observe them all at once. And so what we can do is we can say that this is in fact a multidimensional Gaussian distribution. I can write that my entire vector of observations y, I'm going to put a line under it to denote a vector. I can say that this is distributed as a multidimensional Gaussian with a certain mean. This mean is now a vector, right? It's the vector of all the means of those individual points. And this thing called the covariance matrix. So this is the multidimensional generalization of the variance. This is called the covariance matrix. Okay. In the simplest case, which is the case that we're considering here and is the case that most people are familiar with, this matrix here is a diagonal matrix. And specifically, the entries on the diagonal are just the variances of each of the components, of each of the data points, or each of the dimensions of the Gaussian. And so in this example here with this data set, right? So let's say that this first point has standard deviation sigma 0, this one has sigma 1, this one has sigma 2, and this one has sigma 3. My covariance matrix in this case is just a diagonal matrix that looks like that. And so everything on the off diagonals is 0. A lot of times, our error bars are constant over time, right? So this is true of Kepler data approximately, right? So or even test data. The uncertainty doesn't really change that much over time. And in that case, so sometimes it's as simple as my covariance matrix is just some value, sigma squared, just in a search for all points, times the identity matrix, which is the matrix with just ones on the diagonal and zeros elsewhere. So this is the simplest case. Now, let's think about how to write down the expression for a multivariate Gaussian, right? So if we recall up here, this here is the functional form for a one-dimensional Gaussian. Now, the thing about probabilities is, if you're thinking about the probability of multiple things simultaneously, so for example, I'm observing a data point, there's a probability that I will observe it to be a certain value. If I observe 2 data points, and I want the probability of observing those 2 data points to be those values that I measured, I'm going to multiply those 2 probabilities. Probabilities are multiplicative in that sense. And so in this simple case where my covariance matrix is diagonal, which is the case here where you just have data with error bars and there's no correlation between those data points, then the probability distribution for that Gaussian is just the product of the individual distributions for each of the data points. And so in that case, I can write that the probability of y, and in this case, y of vector, conditioned on the mean vector and the covariance matrix, this is, okay, so I can, write this out in full. It's 2 pi sigma 0 squared times e to the minus 1/2 y0 minus mu 0 sigma 0 squared. That's for my first data point. That's probability of observing my first data point to be a certain value, times 1 over square root of 2 pi sigma 1 squared e to the minus 1/2 sigma 1 minus mu 1 over sigma 1 squared. That's for my second data point, and so forth. And I will do this n times, where n is the number of data points in my data set. I can write this as a product, right? So I can say that this is the product from n equals 0 to n minus 1. And so I have 1 over the square root of 2 pi sigma n squared times e to the minus 1/2. And now, when you multiply exponentials, the exponents sum, right? So there's that neat property of the Gaussian, is that the stuff in the exponent will just sum. And so you have the sum from n equals 0 to n minus 1 of, my observation at the nth point minus the mean at the nth point minus standard deviation squared. Okay, this is the expression for the probability function for a Gaussian in multiple dimensions. There is a much more convenient way to write this, using the notation of the vectors and matrices, right? Actually using the covariance matrix notation here. And this is, I'm going to point out right now, exercise 1 in the Jupyter notebook, is to show that I can write this probability density function as 1 over the square root of 2 pi to the n, okay, times the determinant of the covariance matrix. So again, this is just the normalization, which in many cases doesn't matter, right? It's just the proportionality constant that causes the distribution to integrate to 1, times e to the power of minus 1/2. And here's the cool part. I can write this very compactly without any sums or any products as just a vector matrix product as follows. Okay, so this here is the important result. This is the general expression for multivariate Gaussian. Now you can see that we derive this in the case where sigma is diagonal, right? And so this sum here is really just replaced by a vector matrix vector product, which ends up just being a sum over all the n data points. And again, in exercise 1, you derive this. Now the cool thing here is that we derive this for the case where sigma is diagonal, right? Or the case where you don't have covariances or correlations between your data points. But it just so happens that this expression is completely general. This is the general case, and it works even when big sigma here has off-diagonal elements. Those off-diagonal elements are the key to Gaussian processes. So it's the correlation between data points, or the correlation between parameters. That's what the Gaussian process is modeling. So let's talk about covariances. So what does it mean for you to have off-diagonal elements in your covariance matrix? Well, let's go. So in order for us to understand that, let's first consider the simple case that we talked above, where we have a covariance matrix with no off-diagonal elements. And let's just do this in 2 dimensions to keep it simple. If I have a covariance matrix that looks like this, what I'm saying is that my variance along the first dimension is 1, my variance along the second dimension is 1, and my covariance, which is the correlation between those 2 dimensions, is 0. So if I were to plot this Gaussian distribution, this is in 2 dimensions, so it's a little harder to plot on a piece of paper. But what we can do is plot contours of this probability distribution. Okay, so in this case, let's consider dimensions 0 and 1. So these could be your first and your second data point, or they could be 2 parameters that are jointly distributed as a Gaussian. And let's say that there's some mean, right? So the mean is for y1 is here, and the mean for y0 is here. And so the peak of the Gaussian is right in the middle. Now the probability contours corresponding to this covariance matrix are circles. And you can imagine that if I were to actually visualize this in 3D and rotate it, it would look like a hill. It would look like a bell curve, but just in 2 dimensions, right? It's like a full-bodied bell curve. And so this here, right? So like when we're looking at a probability distribution in multiple variables at once, this is usually called the joint probability distribution. It's the probability of y0 and y1. Now, one useful thing to do is to collapse this probability distribution along one of the dimensions. And so if, for example, I were to rotate this and look down along in the direction of y0, I would see that along that dimension, it's just a Gaussian, it's just a familiar bell curve. And the same thing is true along this dimension, right? It's Gaussian, in fact, with standard deviation equal to 1. That's what we're specifying in the covariance matrix. Well, the variance is 1, but the square root of 1 is 1. So that's convenient. And along this dimension, same thing. Standard deviation or variance of 1. Okay, and now this process here of collapsing the distribution into one dimension is called marginalization. And so this here is called the marginal distribution. This is the probability of the variable y1, regardless of whatever value y0 has. You've integrated that y0 out. So, right, I've introduced two terms here for multidimensional Gaussians. We have the joint distribution, the marginal distribution. There's one more term that we should be familiar with, and that's the conditional distribution. And so quite often, this happens a lot in science, is they're correlated parameters, right? So like, you know, let's say you're fitting a spectrum of a star, and you get some constraint on the mass of the star and the radius of the star, say. And so you publish some result, and you say that the mass is, 1 plus or minus 0.1, and the radius is 2 plus or minus 0.2 in some units. Quite often, a different study will go and refine the mass of the star. Now you have a much better precision for the mass of the star. And so quite often you want to condition your value of the radius on that new information. And so the process of conditioning is, well, I have some probability distribution in many dimensions at first, but now I have extra information along one of those dimensions. And so the question is now, what extra information does that give me about the other dimension? That's the process of conditioning. In this case, the answer is it won't give me any information, and let's see why. So let's plot this again. Okay, so this is just the same plot as right here. I'm just redrawing it for clarity. Okay, and so the thought experiment, that's the word, that that we should think about right now is, let's say that I have this joint posterior or joint probability distribution for y0 and y1, but let's say afterwards I pin down the value of y0. I know it to be exactly here, right? So I've measured it, and I've essentially collapsed this probability distribution to a delta function. I no longer have any uncertainty in y0. This is an extreme case, but let's just say that's the case. I no longer have any uncertainty in y0. This region of parameter space here and here, I can now rule out, right? Because I know the value of y0 to be along this red line. And so the value of y1 is going to be dictated by the value of the probability distribution along that line. Unfortunately, because these dimensions aren't correlated, if I actually collapse this distribution along the y0 axis, I still get that same Gaussian with a standard deviation of 1. Okay, so that doesn't change anything in this case, but I just wanted to point out that this is called the conditional distribution. Right? This is now how you would write this as the probability of y1 given a specific value of y0, because now you've brought in extra information, say from that study that pinned down the mass of the star. Okay. Let's see. So let's take this to the next logical step, and let's add a little bit of covariance in these dimensions. So what I'm going to do now is to say, well, let's consider the case where my covariance matrix, we still have a variance of 1 along each of the dimensions, but now let's introduce a little bit of covariance in the off-diagonal terms. So I'm doing half here. Note that in general, this value has to be the same as this value. That's because this top value here tells me what the covariance of y0 is with y1, and this value here tells me what the covariance of y1 is with y0. those are the same thing. And so covariance matrices are always symmetric about the diagonal. You also typically can't have a covariance larger than the variance. That's not a valid distribution. But let's look at what these contours look like now in that same space. So if I plot the same things before, which is a bird's eye view of the probability distribution, I have y0 here. I have y1 here. I'm actually going to move this over here so that I have a little more space. Okay. Now that I have covariance, what this means is that my contours are no longer circles. Covariance has introduced a preferred direction. And in fact, the fact that those entries are positive means that those two variables, y0 and y1, are positively correlated. And so that means that if I observe, say, the value of y1 to be large, the value of y0 is also going to be large. They vary jointly, they covary. And so we now know that the contours are going to be along this preferred axis. And so in fact, this is slightly exaggerated, but let's just go with it because this is a good example of covariances. My contours now might look something like that. Okay, this is still multivariate Gaussian, so these contours are now ellipses. Okay, along any of the axes, it still just looks like a Gaussian when you compute the marginal probability distribution. And in fact, because the variances, right, the diagonal terms are still 1, the marginal distribution has not changed. The marginal distribution is always just given by the entries on the diagonal. Okay, and so that would mean that standard deviation of this guy is 1. Standard deviation of this one is also 1. However, right, and so let's say this again, right? This is the joint distribution. This is the marginal distribution. The interesting thing is when we consider the conditional distribution. And so perhaps you can already tell what's going to happen here, but let's do it anyways. So I'm just going to, in fact, you know what I'm going to do? Because I'm on an iPad, I can just duplicate that to here. Erase some of the stuff, erase some of that. Okay, let's consider the same thought experiment as before, where suddenly I know more information about y0. Let's say specifically that I know that y0 lies somewhere along, or y0 has this specific value, right? So like I now collapse my probability distribution to get delta function here. What do I know now about y1? I haven't made any additional measurement of y1. I've measured something about y0, but because they're correlated, I now know that y1, the probability distribution for y1, restricts it to somewhere along here. And so you can see that two things happened. First, if I were to just plot what the Gaussian looks like along this line here, I'm going to get something that looks like this. So the bewildering thing is that the mean of y1 changed, right? It used to be right in the center. But by observing something about y0, I now know that the mean of y1 has changed. The other thing that's changed is the variance, or the standard deviation of the conditional distribution of y1 is smaller, right? So sigma conditional is smaller than 1. So that's what's cool about correlations among variables. That means that by observing one variable, if it's correlated with another one, I've gained information about that one. This is not too different from, like quantum entanglement or something that you might find in quantum physics, where observation of one thing gives you information about the other one. This is similar to entanglement, but not definitely not a quantum phenomenon. It's just a statistical thing. Now, exercise 2 in the Jupyter notebook as you explore a little bit more of this. As you plot some of these joint posterior distributions and look at how varying the covariance changes the shape of these things. Okay, so we talked about Gaussians for a while, but let's go back to GPs. And I mentioned earlier that a GP is a Gaussian, essentially in an infinite number of dimensions. That's true. It's one way to think about it. Let's think about it a slightly different way, though. And the way that I like to think about it is a Gaussian process is a Gaussian distribution, not over variables, not over points, but over functions. So a Gaussian process is actually a family of functions that have a certain covariance structure. And so if I were to, when I sample from a Gaussian, which is something that you should have done by now in the Jupyter notebook, I'm picking values for individual points or values along individual dimensions and plotting these histograms. But with a Gaussian process, your samples are functions. And so if I have a certain Gaussian process with a certain mean and a certain covariance, samples from that Gaussian process are going to look, for some value of mu and sigma, they're going to look like that, like that. There's an infinite number of functions specified by any Gaussian process. The thing about these functions, they're all different, but they share the same covariance structure. And what we're going to see in a second is just the smoothness, the length scale on which these functions vary, the amplitude of these functions. Those are the things that are shared across these functions. Okay, and so like I said, it's a Gaussian process is a Gaussian distribution over functions. Okay. And typically, right, so if I have some data set Y that I want to model as a Gaussian process, I typically say it's distributed as a GP with a certain mean and a certain kernel. Now, these are directly related to the mean and the covariance of a Gaussian, except that in this case, the mean is a function and the kernel is also a function. These are functions. All right, that's why they have slightly different notation, but this is very much mu and sigma, except that this time they are functions. We'll talk about that in a second. But back to the point about how these curves all have similar statistical properties. I just want to talk about how correlations can be used to think about functions, right? So if I have a data set or maybe a sample from this Gaussian process, might look something like that, right? And let's say this is y, the function of time or whatever. Okay. Now, if I look at any 2 points, pick any 2 points that are close together. Okay, so they have they're separated by some delta t, right? So like I can look at those 2 points, or I can look at these 2 points and so forth. Okay. They're going to be close to each other in y value, right? So like this particular function, which was drawn from a particular Gaussian process, is one with a certain length scale. That length scale is larger than this delta. In this case, it's time, so it's a time scale. And that time scale is much larger than the delta t that I drew. What that means is that points that are separated by a delta t that's small compared to that time scale are going to effectively have the same value. They're very close to each other. On the other hand, so let's use a different color here. So I'm going to use green. So if I have a point here and a point here, and these are separated by a much longer baseline, their values have nothing to do with each other, right? Like I can't, knowing the value here doesn't let me really predict all that well what the value over here is, because the function has just gone off and done its thing. That's not the case for the red points, where knowing the value here gives me a very good idea of what the function is doing here, right? If I masked all the other data, you could probably predict the function was going to keep going up here, right? So like at this point. So the way to formalize this is to say that points on time scales that are very short have a large covariance. And points that are on time scales that are very long have a small covariance, or a covariance that's close to 0. Okay. And so you can kind of start to think about how a covariance matrix might inform something about the scale in which these functions are allowed to vary. And in fact, this kernel function here, right? Most of the time when you're using a Gaussian process, what you have to do is decide what kernel to use. You could use anything, but typically the kernels that we think about in astronomy typically look something like this, right? So like this is the value of the kernel as a function of the time difference or the length difference or whatever your x-axis variable is of a function of delta t. Typically, the covariance functions that we think about look kind of like this. And in this case, this is also a Gaussian by coincidence. But the point is that, so this would correspond to delta t of 0, okay? Or in some sense of the word, this is now, this is the future, so positive delta t, and this is the past, negative delta t. So points that are close in time to now are very correlated to what's happening now, right? So if I know the value of the function right now, I can predict very well what it is in a split second from now or a split second ago. But as I go into the future, as I go into the past, I lose the ability to predict, right? They become less correlated. And so a typical covariance function that people use, there are several, but one of the most common ones is a function of, it can be a function of delta t, or it can be a function of 2 different time points, and it's really a function of their difference. And it's this, right? So typically it's written this way: e to the minus 1/2 ti minus tj over L squared. And if this looks familiar, it's because it is. This is a function of a Gaussian. But because we've used Gaussians in several different contexts already, we call this the squared exponential in order to stop overloading the word Gaussian. So this is the squared exponential kernel. There are other ones, and you will see them in the notebook. But we're gonna mostly just talk about this one because it's very convenient. And this squared exponential kernel has 2 parameters. It has an amplitude and a length scale. And again, this could be a time scale too, especially if our axis is time. It makes more sense to talk about this as a time scale, but it's the same thing. Now, notice that so right, this kernel is a function, but in practice, computers can't evaluate functions, right? So like a function as a mathematical object is this continuous thing that's defined on the entire real line that's valued everywhere. But whenever you're dealing with data, you measure that function at specific places. And even when you're plotting a smooth function, you go into matplotlib and numpy and you create an array that has enough points in it, like 1,000 or 10,000, to trick the eye into seeing something smooth. And so I said earlier, a Gaussian process is a Gaussian in infinite dimensions, but that's never realistic, right? You're never going to be able to truly evaluate that Gaussian in infinite dimensions. And so in practice, you're always just evaluating this Gaussian process at a large number of dimensions, but something like 100 or 1,000, however many data points you have. In that case, it's really just a Gaussian, right? Like, there's all this mathematical formalism behind the mean function and the kernel function, but at the end of the day, you're using that to compute the covariance of a Gaussian. You're using that to compute the mean of a Gaussian. And so, remember, my covariance matrix specifies the covariance between all points in my data set or between all pairs of variables. And so this here is the, so this first entry is the variance of, T0. This here's the variance of T1 and so forth. And the off-diagonal entries are the covariance between T0 and T1 and so forth. In order to compute these entries, if I want to use this Gaussian process with the exponential squared kernel, I just compute the value of the kernel at T0 and T1, or compute the value of the kernel at T1 and T1. That's the prescription for constructing this covariance matrix. By the way, so we have arrived at exercises 3 and 4. Okay, at this point in the lecture, where you actually compute this covariance matrix and look at what it should look like. And so, this is a giant matrix, typically, if you have a data set of 1,000 points or something. And so I'm not going to write out what it looks like, but we can try to kind of visualize it just by noting that if you have a kernel that looks like this, the maximum covariance is happening along the diagonal, because the diagonal are the indices where I equals j, right? Sigma ij, where I equals j, a delta t of 0, because it's the covariance between a point and itself. As you go farther from the diagonal, that covariance drops. And so if we actually plot an image of this covariance matrix, you would get a really bright feature here. And then, you get something that drops off exponentially towards the edges. And so points here are highly correlated. Points over here are uncorrelated, right? Their covariance drops off to 0. Exercises 3 and 4 will help you visualize this. It's hard to draw this on the blackboard. Okay, so let's think of an example, right? So like I introduced this exponential squared kernel, and it has 2 parameters. It has an amplitude and a length scale. Let's get a sense for how changing that amplitude, changing that length scale, changes the kinds of functions that this Gaussian process represents. So let's go here. Let's write an example. And let's consider functions, but really vectors, because we're doing this in a finite number of dimensions, that are drawn from a Gaussian process or a Gaussian distribution with mean mu, let's just say that's some constant, and a covariance that's computed from the squared exponential kernel, given a value of the amplitude and a value of the length scale. Now let's do this for a fiducial case for a certain value of a, say it's a naught, and a certain value of L, let's say it's L naught. And let's just draw functions, right? So, I don't have any units on my axis, so I don't have to worry about telling you what a naught and L naught are. But let's just say these are functions that are smooth and vary on a certain time scale. That's about half of the length of my axis here. Something like that. That looks a little different, but let's say it's okay. Great. Okay, so let's say that's my fiducial case. Let's now consider the case where the amplitude is much smaller than that original amplitude. And let's keep the length scale the same. All that's going to happen is the amplitude of these features is going to decrease. And so you're going to get, if you draw samples from this Gaussian process, you're going to get curves that vary on a similar time scale, they do similar things, but their amplitude is smaller. And by the way, so I didn't point this out earlier, but like the mean of the Gaussian process is mean at somewhere. Again, I don't have units. This is just qualitative. Okay, so the amplitude really just controls the amplitude of these curves. So that's intuitive. And obviously, if you increase the amplitude, the reverse happens. Let's consider then the case where the amplitude is my fiducial value, and my length scale is much smaller than than my fiducial length scale. In that case, right, so same use here. Let's draw some of these. What I'm saying is the length, or the time over which the values of the function can vary significantly is now much shorter. And so now the function can be a lot less smooth. So in a certain sense, that length scale is really just the smoothness of the function. And so the function is allowed to vary more rapidly because nearby points are less correlated with each other. And so typically, samples from this Gaussian process might now look like this. They have the same amplitude as before, roughly. But now they're just doing, you know, higher frequency oscillations. And these are all just random and stochastic. But you can see that that corresponds to a smaller length scale. Just for completeness, let's consider the opposite case. So still same amplitude, but let's consider a length scale that's much larger than L0. And in this extreme case, you might be able to guess that my function is going to be even smoother than this original case, which means it's allowed to vary even less. And so you might have something like that. You might have something like that. And something like that. And something like that. Okay, and the limit that the length scale goes to infinity, these just become lines. You have no curvature at all. They become just flat lines. Okay. You can explore this a little more in exercise 5. Great. Okay. Great. So, you know, we understand what a Gaussian is. We understand how to draw samples from a Gaussian process, right? You just specify a covariance matrix, and that tells you what these functions are allowed to do. But, you know, one thing that you might be thinking is, well, I want to actually apply this Gaussian process to data. I don't just want to, you know, produce functions out of a hat and stare at them. I want to actually find functions that are consistent with my data. Now, one silly way of doing this is, say, I have some data points, right? Some error bars. By now, if you've completed exercise 5, you've drawn samples from a Gaussian process. And so you could construct the following thought experiment. You can actually do this in practice too. You draw a sample from the Gaussian process. Okay, good. And then you ask, did it go through my data points? If the answer is no, you erase it and you try another one. And then you ask, did it go through my data points? Especially if you have more than just a few data points, the answer to that is almost always going to be no. But if you were to do this, you know, if you had the age of the universe and a supercomputer, I'm not recommending you do this, but you would eventually find the functions that, you know, from this family of functions conditioned on a certain value of the amplitude and the length scale, you would find the family of functions that go through these data points. You know, they're all going to be different, but they're all going to have the same statistical properties, right? The same covariance and the same mean. And so this technique that I'm telling you about is called rejection sampling. In this case, it's a terrible idea because this would take way too long. You would throw out almost all the functions that you sample from the GP. In other cases, this is a powerful technique. But I just mentioned it because this, you know, we can do better. So that's good. So more realistically, right? So let's say that I have, you know, y here, time here, and I measure some points. Let's say that I measure T0, T1, T2, T3. I measure values y0, y1, y2, y3. And then I want to use this Gaussian process to extrapolate, right? I want to predict what the value is at some time that I'm going to call T star. Okay, and this is the same notation that I'm using in the Jupyter notebook. Okay, and this T star doesn't have to be a single point, it can be a vector of points. And so we can say T star 0, T star 1, and so forth. I want to be able to predict the value y star 0, right? I'm going to put a question mark here because I don't know where it is. Y star 1. I want to use the Gaussian process to tell me what this function is going to do at those times. So the thing that we're going to do here is something I mentioned before, is we're going to condition our Gaussian process on these measurements, T0, T1, T2, and T3, the values at those times. And so we're going to compute the conditional value of our function, right? So y star conditioned on the y's that we measured. And by the way, this is exercises 6, 7, and 8 in the Jupyter notebook. And the derivation of this is, it's not all that straightforward. I have links in the notebook to a paper on Gaussian processes that derives this, if you're interested in looking at that, and that has references in there. I'm just going to give you the result, and you're going to code it up in the Jupyter notebook and verify, in fact, that it works. You don't have to worry too much about how it's derived. So I'm just going to say that, you know, the cool thing is that when you condition a Gaussian on data, you end up with a new Gaussian with a different mean and a different standard deviation. Remember, we did that up here. So when I condition my value of y1 on a new measurement of y0, I still have a Gaussian. It's just that the mean changed and the standard deviation changed. And so we can formalize that, right? We can actually write down what this conditional mean and conditional variance is. I'm going to call it mu prime and sigma prime, okay, where mu prime is given by the following expression. Okay, so what this is this is the value of my covariance between my starred points and my unstarred points. And so by the way, but let's just introduce a little bit more terminology here. Because Gaussian processes are used a lot, essentially as machine learning, right? And related to things people do in the machine learning community. These measurements that you condition your data on are called the training set, so the training points. And then these where you're predicting are called the test points. And this is terminology that's from the machine learning community. And so the thing that I underlined here, this is the covariance between my training points and my test points. And then this is just the covariance between my training points. And so you can see that the new mean of my Gaussian process is just a weighted linear combination of my observations, because my observations directly inform the mean of my new Gaussian process. The other thing that we need is the expression for the new covariance matrix. And this is given by the covariance between my test points minus the covariance between test and training data dotted into the covariance of my training points, actually the inverse of that thing, and then dotted into this. So it's sandwiched in between the cross covariance there. That's it. Again, don't worry about how this is derived. This is here for completeness so that you can refer back to it. It is coded up in the Jupyter notebook, and I have you go through it. There are some things that that you should, even if you don't understand how it's derived, there's some things that you can just intuit from it. For instance, the cool thing here is that so just by looking at the sign of this thing, you can glean information about what's happening. whenever I observe data, my covariance always decreases. Okay, that's what that sign means, is that I have my original covariance. This is in fact my prior covariance on my test points, which I haven't observed, right? I don't have data for the test points, which is why I'm predicting there. And so all I have is a prior with some covariance. The actual covariance, when I condition on the data that I observed, goes down. And that makes sense because what you know is a combination of information from your prior and from your data. And whenever you observe data, you shrink uncertainties, right? Adding data always reduces variance. Okay. The other thing that you can intuit about the mean here is if I test the value of my Gaussian process on the training points, meaning if I set t star equal to t, so I predict the value of the Gaussian process on my training points themselves, you'll notice that I get sigma of t comma t times sigma inverse of t comma t times y, or dotted, sorry. A matrix times its inverse is the identity matrix. And so this just gives me y. And so my new mean is just the original mean. Or is just the data, sorry, right? Because I've told the Gaussian process, I've observed the value of this function to be right here. And so the Gaussian process will go through that point. This, by the way, is in the limit that you have no uncertainties, right? This is actually in the limit where your error bars are 0. If you have finite error bars, this is, I think, exercise 7 or 8, then this mean is going to be, you're going to have to account for that. Your Gaussian process is not going to go exactly through that data point. There is going to be variance. Okay. Great. So we're almost done here. We've talked about Gaussian processes, how to use them to predict data. These exercises here. There are 2 more things that I want to do, and these should be fairly quick. The first one is tuning the GP. So, we've picked a kernel function. In this case, we picked the squared exponential kernel. But so far, I haven't told you how to figure out what the amplitude and the length scale is when you're modeling a data set. And so in exercise 9, what we're going to do is I give you a data set and you compute the probability of your data conditioned on different values of the length scale of the GP. And then you just maximize that probability. You just look at where the peak probability is. And in fact, you can get an entire probability distribution, which is your constraints on what the length scale of the process that generated that data is. And so that's exercise 9. And all we're doing is just recall that our probability function is given by this expression here. So I'm just going to copy this down here. Just for completeness. Okay. Okay, so this again is the probability of y conditioned on mu and sigma. Okay, and so specifically, it's useful to point out that sigma here is a function of A and L. And so this probability here is really a probability of y conditioned on some mean mu, which I think in the examples that mean is 0. But as we'll see in a second, that mean can be a function too. So conditioned on mu, A, and L. Okay, and so in exercise 9, what we're going to do is we're going to just simply, use this formula to compute the value of the probability by varying L. And so what you're going to get at the end is, given a data set, so by the way, the data set, let's draw that, might look something like, you observe some noisy data and it goes up and back down and then up and back down. There's some characteristic length scale there. And so what you're going to compute is the value of the probability for different values of L. And you're going to build up a probability distribution, P of Y given L as a function of L. It's probably going to look like a Gaussian. Gaussians are everywhere. Gaussians all the way down in everything I do. And so that's going to have some mean value and some standard deviation, and that is your posterior belief, posterior constraints on what the length scale is of the process that generated that data. In exercise 9, we're assuming that we know A and that we know mu, but in general, you're not going to know it. And so what you have to do is compute this probability, varying A, varying L, varying mu, and any other parameters of your model. You could do this the brute force way, right? By gridding up all those parameters and then computing the probability. In general, if you have more than 2 dimensions or more than 3 dimensions, it's computationally intractable. And so to do that, you have to turn to something like MCMC. And that's what exercise 10 is going to be. It's the last exercise in that notebook. And that brings us finally to inference. We're already talking about inference, but let's talk about a slightly more general case. So this is in exercise 10. We have some physical thing that we want to learn, right? Like we have, it's different from exercise 9, where all we have is some data set. We assume it's generated from some process, and we're interested in the length scale. More generally, you're going to have some data set that has some signal that you know how to model, like a transit or a flare, or like some sort of like a gravitational wave. And you have a function for that. But there's extra stuff. You want the GP to capture that extra stuff while simultaneously inferring something about the model parameters that you actually do care about. And so in exercise 10, the activity is to fit for the slope and intercept of a line. So for instance, this could be, you have some measurements of the expansion velocity of the universe as a function of redshift, but it's in the presence of a bunch of noise. And so you want to fit a line to that to infer the Hubble constant. But you want to do that with the GP so that you're capturing the correlated noise that might be biasing your measure. An alternative example, and this is the exercise in the second notebook, is if you're fitting a transit. And so let's use that as an example. It doesn't really matter what your physical model is, but let's say that, as I mentioned earlier, if you had a perfect detector and stars never varied, you might observe an exoplanet transit to look something like this, and you'd measure it perfectly. And the physics, or the things that you want to infer, are maybe simply the time scale, right? How long the transit lasts, the depth of the transit. Okay, that tells you something about the size of the planet. And then the time of the transit, which can tell you about the period of the planet, or if that's varying, it's not periodic, it can tell you about the presence of other planets in the system that are pulling on it gravitationally. It doesn't matter. You have some parameters that you want to infer. Unfortunately, like I said, that's not the observation you make. The observation you make is this. Okay. The star is varying, or maybe there's detector systematics. You can kind of see the transit, but now it's not so clear where the transit center is, right? Like, is it here or is it here? You don't know. And then the duration of the transit, is it from here to here? Or maybe does the transit start here and go to here? You also don't know. And similarly with the depth. If you were to just fit a transit model and nothing else, you'd probably get the wrong answer, because those wiggles are going to screw up the fit. So more generally, what you want to do in a GP inference problem is to compute the probability of y conditioned on, so the probability of your data, right, conditioned on the things you care about. These are your model parameters. And in the case of exercise 10, this is the slope and the intercept of the line. And you want to simultaneously condition it on the GP parameters. Which in many cases, you don't care what they are. You have to infer them so that you can marginalize over them. Okay. And so again, this probability is really just, you know, your Gaussian likelihood, right? So it's the expression that you've seen a million times before today, y minus mu transpose sigma inverse y minus mu. Now, as before, sigma is computed from your kernel, right? Sigma is a function of A and L, which is computed from your kernel. You know, let's say K, computed from your kernel. And then when you have this extra physical model, that is your mean function, right? So like the thing that you're observing is that transit model plus a stochastic component, which is captured by the covariance of the Gaussian process. So this mean here is just, you know, whatever function of your physical parameters. So it's a function of the depth, the time scale, and the time of transit. And you know, in the exercise in the second notebook, this is, believe it or not, just the Gaussian, right? So I think that's the 6th time I use a Gaussian in a different context, but the transit kind of looks like an upside down Gaussian. But anyway, so in exercise 10, as well as the exercise in the second notebook, we have something like, in this case, 5 parameters, 4 or 5 parameters. And so that's slightly too much to do this brute force grid search, where you compute the probability for every combination of those variables. And so we're going to use a Markov chain Monte Carlo sampler to approximate what this posterior probability distribution is, right? So what you're trying to find is the probability of the depth of the transit condition on your data, the probability of the time scale of the transit condition on your data, and so forth. Those are the histograms that you get out when you plot a corner plot of your MCMC samples. The tutorial should guide you through how to do this using the MC package. The MC package has very good documentation that you can check out if you're unfamiliar with MCMC. You can also look at the answers. That'll guide you through it. But if you have any questions, do email me. Again, my email is robbluebeer@gmail.com. And I'm happy to point you to other references using MCMC. That's pretty much it for this lecture. So you now have everything you need to be able to go through all the exercises in the first notebook, and for you to be able to answer the one exercise in the second notebook, which is a little more involved. That's about it. So just to recap what we learned today. So a Gaussian process is formally, it's a Gaussian distribution in an infinite number of dimensions. In practice, that's useless because, you know, computers can't compute things in infinite dimensions. And so in practice, Gaussian process is really just a Gaussian distribution in a bunch of dimensions. And those dimensions are typically your data points, right? So you're computing your Gaussian process for your data, right? So if you're using it to interpolate missing data, extrapolate, or for inference, right? You're using the fact that the Gaussian process comes equipped with a probability or a likelihood, right? It's the likelihood of the data conditioned on the parameters of that Gaussian process. So we're using that to actually infer what the probability of our model parameters are given our data. And by the way, I never explicitly mentioned this, but implicitly we've been using Bayes' theorem all along. And so if you're interested, look up Bayes' theorem. And I believe Adam may have introduced this briefly, but the basic idea is that the probability of your model parameters given your data, which is what we want to compute when we do MCMC, it's proportional to the probability of your data given your model. That is what the Gaussian process gives you. It gives you the likelihood function, probability of your data given your model, probability of y given the amplitude and the length scale. Formally, the other constant or the other factor in Bayes' theorem, the proportionality, is your prior. So this here is your posterior. This here is your likelihood. That's what the GP gives you. And this here is your prior, any prior information you have about your model parameters. This can be a uniform prior if you don't have any information, or it can be a Gaussian prior. If, say, someone else has observed this star and knows the mass of the star to be a certain range, you can use that as your prior. But that is pretty much it. So again, good luck with the worksheet. Email me if you have any questions. Feel free to reach out, and the answers are there in the repository. So I look forward to seeing all of you guys in a couple weeks. And until then, have a good one.